Okay, physics time. We're talking about momentum and impulse. So the first thing we want to talk about with momentum is one of the three universal principles, actually one of the three fundamental laws of the universe, and some people might say the only three fundamental laws of the universe. In the same way that we have 3 or 4 fundamental forces, there are 3 fundamental laws. And the 3 fundamental laws are the law of conservation of energy, which we talk about, we will talk about in here, we talk about in physical science, we talk about it all the time in chemistry, the law of conservation of momentum, and the law of conservation of angular momentum, which is what we talk about when we talk about angular momentum. The difference between momentum and angular momentum is that an object moving in a straight line has momentum, an object spinning or revolving has angular momentum. And those are always conserved. We can think about it as the total amount of energy in the universe is conserved, the total amount of motion in the universe is conserved, and the total amount of torque or twisting motion, in the rotational motion in the universe is conserved. So what we're worried about today is the law of conservation of momentum. It's got an extremely simple equation. P initial equals P final. That's it. The initial momentum is equal to the final momentum, period. Remember that momentum is a vector quantity and has direction. So the direction is also conserved. Meaning, if I have 2 equal mass billiards balls, and they have the same speed, but in different directions, how are their velocities similar? They have the same speed, but different directions. Are their velocities the same? No, but their speed is the same, and so we're going to draw in time one, they are moving in this way. These are both velocities. We'll say velocity initial 1 and velocity initial 0. So that's, velocity initial 2. So v sub naught sub 1, v sub naught sub 2. And then at time 2, what happens? Well, do their masses change? No. What must be true of the momentum? What must be true of the momentum?
It's the same.
It has to stay the same in time 1. We couldn't even call this. Let's call this time 0, and let's call this time final. Time not time final. So what must happen? Well, if their masses don't change, which they don't, because this is what we call an elastic collision. If their masses don't change, then in the next time they just switch. They just switch their velocities. V sub F1 and V sub F2. If they were billiard balls or bowling balls or cars on a track, like cars on an air track or air hockey track pucks, they're coming in like this, they collide, and then they bounce off like this. What if one is stopped? Same thing, they just switch. Momentum is conserved. Now what happens if instead of, this is called what kind of collision? Elastic, meaning that they bounce. There's a more specific physics definition which your book talks about, and it is that energy is not lost in the collision, or energy is not removed from the system as sound or friction or deformation. In real life, obviously, if billiard balls are colliding, there is going to be some sound, there's also going to be some friction, there's also going to be some deformation. But if we negate those things, that's called an elastic collision. In fact, this relates to the gas laws of physical science. If we assume the atoms are behaving this way in a gas, then we can assume multiple other truths about gas laws. I have videos about gas laws you can watch if you're interested. So what might be true about an inelastic? We're going to start from the bottom this time. Inelastic collision. Is momentum still conserved?
Yes.
Yeah, it's a law of the dang universe. So P sub naught still must equal P sub F. That has to be true. But let's say this time we have time equals 0. The example your book gives is of a fish eating another fish. I like this one, but let's use instead, because it's on your test, 2 pieces of putty. So instead of billiard balls now, they're putty. We'll say they have the same mass again, and they're moving in the same way that the billiard balls were in the first one. Okay? So what's going to happen? What's going to happen if these collide? Well, instead of bouncing elastically, what is going to happen? They're going to do what? Instead of switching momentum, their momentum is going to, you guess, if they're putty and they're moving at each other like this, what's going to happen with the putty?
They're going to hit and stop.
Hit and stop because they have done what?
Melted together. Melted.
Collide. They've become one thing. So now we have a ball with twice the mass
Melted wasn't the word.
moving with the velocity of both of them added together. So if we add these two velocities together, and since it's vector addition, so what is the addition of these two velocities? Velocity equals 0. Momentum is still conserved. They have the same momentum added together. So what's the total momentum here?
The same, so that.
Yeah, the sum of the p here is 0.
No.
What's the sum of the p here?
0.
0. What's the sum of the p here?
0.
0. And what's the sum of the p here?
0.
0. So we really have two options. If it's perfectly elastic, then they just bounce. If it's perfectly inelastic, they collide to form one thing with a combined mass. Questions about elastic and inelastic collisions? Questions about the law of conservation of momentum? Levi? No? The math for this does kind of get, I wouldn't say hard, but it does get a little bit complicated. Let's look real quick in your book at practice problem. We're not going to do it on the board because we don't have time, but look at problem 9, or page 97, this problem solving. Look at page 97, the problem solving box. Consider, no one's listening to me, consider, you can watch on the video though, I guess. Consider a 6 kilogram fish that swims around and swallows a 2 kilogram fish that is at rest. The larger fish swims at 1 meter per second. What is the velocity immediately after launch? So what's happening now, what kind of collision is it, first of all? Inelastic. And so we're going to have the same momentum after, except now what's going to change? The what?
The velocity.
No? Well, the velocity will change, but because what other thing has changed?
The mass.
Mass, yeah. The total momentum is the same, but now it's a larger mass. So will it be moving slower or faster after launch?
Slower.
Slower, because it must have a lower velocity, because we have the p has to stay the same, and so if the mass increases, the velocity must decrease. Okay, that's an example of an inelastic collision. So we're all about p naught equals pf, but usually we actually have to write it in this way. Watch this. We usually have to write it because this doesn't change. The only things that do change are the things that make it up. So usually we're more about m sub naught times v sub naught equals m sub f times v sub f. Why is this the same as that? Well, because p equals mv. Transitive property. That makes sense, right? If p is equal to, if p sub naught is equal to f sub naught, sorry, p sub f, then we just substitute p with mv. So m sub naught v sub naught equals m sub f v sub f. That's the law of conservation of momentum. It's not complicated. It's one of the foundational principles of the universe, but it's not complicated. Probably because it's one of the foundational principles of the universe, it's not complicated. In fact, physics in general is not complicated. I don't know if that's what you're finding so far, but it is true. Momentum. Okay, now we're going to talk about impulse, which is different from momentum. Oh, by the way, what do we measure momentum in? Sorry.
Newton seconds?
Newton meters. Newton meters. Am I right? No, sorry, kilogram meters per second.
Oh, yeah.
Kilogram meters per
Impulse
second.
is Newton second per kilogram.
Yeah, kilogram meters per second. Newton meters per torque. I was confused. Oh, and momentum is what kind of quantity we already said?
Vector?
Scalar or vector? It's vector. And so is it possible there will be vector addition by trigonometry in your test? Yeah, because but we're not going to go over that again, because we already have for forces, we already have for velocity, and we already have for vectors in general. But recognize the momentum can be added in the same way that vectors can. And since mass is in there also, you might have to find the momentum using vector addition, and then find the new velocity by dividing out the mass, which is not complicated. It's just, I don't know, maybe time consuming. Okay, so impulse, J equals Ft, where J is what? You just impulse? Yeah, J is impulse. Well, we'll talk about what's measured in a second. F is what?
Force.
Force measured in
Newtons.
and T is
Time
Time.
per second.
measured in seconds. So what would impulse be measured in?
Newton seconds.
Newton seconds. Look, this is the same thing as a kilogram meter per second. So what's a Newton equal to? Do you remember?
Kilogram.
A Newton is a kilogram times meter squared per second squared. Wait, something's wrong here. Because those don't. Oh, not meter squared. Sorry, a joule is a kilogram meter squared per second squared. There we go. This is true. A Newton is a kilogram meter per second squared. Remember, F equals MA. So a Newton is a kilogram meter per second squared. And then momentum was what?
Kilogram meters per second.
Kilogram meters per second, or we can write it as kilogram meters per second. So if we just multiply this Newton times seconds, which is what we have here for impulse, it's the same thing as kilogram meters per second. What does that tell you about the relationship between momentum and impulse?
They are very similar.
Yes, they are. In fact, here's another equation for impulse. You have to know both of these because it depends on what you have, which one you use. J also equals delta P, where J again is impulse, P is momentum, which is measured in kilogram meter per second. And then just to keep them straight, we usually still measure impulse in Newton seconds. Obviously, the units would be the same. But there's a difference because we're talking about change in momentum, not just momentum. So depending on what you're given, you will use either J equals Ft or J equals delta P. J is also a vector quantity, so it's force. Impulse is also a vector quantity. One thing that impulse teaches us, let's do a problem with that, or just a little conceptual problem with that. One thing impulse teaches us is that what you're really doing in a collision is talking about change in momentum. What is change in momentum? What is the definition of change in momentum? Or like, what is the term for change in momentum? Impulse. So what we're really talking about when momentum changes is impulse. What we're really talking about when we talk about collisions is impulse. Give me an example of a collision.
Bull runs into a human.
Okay, good. Oh yeah, that's looking like an alien bull of some kind or other, but
Give it a knife for a horn.
there we go.
Yeah.
It's got 3 eyes. Bull runs into a human.
Oh, that's a big human.
Well, it's a small bull, the alien bull. Bull runs into a human. Instinctively, not just because the bull is scary and has 3 eyes, but would you, the bull will hit you. You're not running away to escape the bull. The bull will hit you. Would you, in order to decrease your injuries, which is what people like to do, would you go at the bull or would you back away from the bull? You'd back away. That's because, just instinctively we do it, but it's actually physically because of J equals Ft. Because if you run into the bull, what are you doing about the time of the collision? What are you increasing here? The force. If you decrease the time of the collision, the same J is going to happen no matter what. Same J. If you decrease the time by running at the bull, what does that do? Increases the force. Whereas if you lengthen the time, it decreases the force.
Okay.
Since you're a little baby, I have a little baby, and since you're a little baby, you know that falling or hitting a soft thing is better than hitting a hard thing. But this is the reason why. Because what really is happening when you hit something soft is you're increasing the time you're in contact with it. You ever punch a wall, Levi? Ty, you ever punch a wall?
Yeah.
I bet you do. What's a better wall to punch? Brick wall or drywall? Drywall, because of this. You're increasing the time you're touching. Because the drywall does what when you punch it?
Collapse.
Yeah, it collapses. And so you're touching the drywall, not only for the time that you're actually first in contact with it, but that it gives with you, and so it's in contact longer. But you punch a brick, does the brick collapse? No. And therefore, it's this one. Bad. Good, or not always good. You shouldn't punch walls. Moral of the story. There's a question on your quiz about, or a question on your chapter review about why do car dashboards have a cushion on them? It's because of this. If your head's going to hit something, you can make a nice looking dashboard out of solid stainless steel. In fact, if you wanted your dashboard to look like a spaceship, there you go. Here's your head. this would be a beautiful dashboard, just stainless steel. But it's going to decrease, or it's going to decrease the time you're in contact with it, and then it'll increase the force, and so you might have no top of your head. So what they really do, and they still look kind of nice, but there's a nice pillowy bit here. Where do you want to hit a dude in the face? Where do you want to hit a dude in the face? To kill him. You want to hit him in the face. No, okay, let's say if your goal is not to harm the dude, but you have to hit someone. This is a saw type situation. Okay. You have to hit someone, but you don't want to injure your hand. Where should you hit them? No, well, maybe if you had it in their head, you don't. You hit them as a human being.
I mean the stomach?
Probably the tummy, because it's soft.
Yeah.
And then the reason it's soft is because it increases the time of impact. Or the buttocks, depending on who it is. You know, there's some people with hard buttocks. Yeah, somewhere with a lot of give. I keep using that word give, but all it's really doing is increasing the amount of time. There's one other thing. Oh, bouncing. Next subheading, bouncing. We all like a good bouncing, don't we? Bouncing, bouncing, bouncing. Here's the physics behind bouncing. Define an impulse for me.
Impulse, force times time.
Try again.
Change in momentum.
There we go. Change in momentum. There's a good demonstration I do with this sometimes that I'll do for you when we're done with the video. Basically, because impulse is change in momentum, and we just discussed how the collision, the impulse, is what we're really worried about when we're having a collision. So if here's you, and here's you in an alternate universe. They're both, okay, for some reason you have different arms in the alternate universe. Okay, here's you and here's you in an alternate universe. In one universe, a pot of flowers with a mass of 1 kilogram and a certain velocity is going to fall on your head. And when it falls, it will break. Okay?
Okay. I accept my fate.
In the second universe, a bowling ball with a mass of 1 kilogram, that's not a very good bowling ball, basketball with a mass of 1 kilogram, with a certain velocity, is going to fall onto your head, and it will not break. It will bounce. Which one is preferable?
One that
Yeah, you're right. The bouncing is actually worse. It seems, this is counterintuitive, but the bouncing is actually worse because what's the change in momentum here? Well, it went from some certain p to, remember, let me do this mathematically actually. Delta p equals p sub f minus p sub naught, right? Same thing over here. Delta p in the non-prime universe equals p sub f minus p sub naught. How did the momentum change? It went from a certain p to what?
nothing.
Nothing. So p minus 0. And this one went from p sub f minus negative p sub naught, right? Or minus negative p sub f, if we assume it's going to bounce with the same velocity it had. So what's your delta p here? Well, minus a negative equals what?
So it's double.
Double. It's almost exactly, without friction, it is double the impulse for something to bounce. A neat example of this is the idea of this, I forget the name of it. There's a water wheel. The Pelton wheel. The Pelton wheel. So up until the invention of the Pelton wheel, water wheels were shaped like this. And so water would hit them and drive the wheel. Aye, aye. And then the Pelton wheel came along and it's shaped like this. And so water would hit them, but they would have to turn around and go back. And so it's double the impulse. It's the exact same force of water, but it would spin the wheel almost twice as fast because of the impulse. And so it would drive the machinery or whatever much, much, much better. So if you're going to get hit in the head with a baseball bat, how can you prevent it from bouncing?
Break it.
Yeah, okay, make them use a baseball bat over it. But if you just move with it,
Yeah.
right? Yeah, it's already instinct. We think it's instinct because I want to move away from the thing that's going to hurt me, but it's actually due to this. I want to increase the contact time to decrease the force. I want to increase the contact time to make sure it doesn't bounce because that will impart twice the change in momentum to me, twice the impulse. The cool example that I do, and I'll just explain it on the video, is that, I've used it with the door before, I've done it with a book that's set up, but I have two things. One, they have the same exact mass, a racquetball, and then a little balloon full of flour. And we have them on the same, we suspend them from the same length of rope, raising them up to the same height, and then we drop the flour sack with the balloon, and the book wobbles when it hits it, and then it stands back up. But when I hit with the racquetball bounces and the book falls down. Or if we do it with the door, we measure how far open the door is. We throw the racquetball at it, and the door opens 20 meters. We throw the sack of flour at it, and the door opens 10 centimeters. Because bouncing imparts more impulse. There's something I didn't stir block in there anyway. Figure it out for yourself. Bye. That was one of the worst videos.